Welcome back. This is section 9.8 on machines, and I believe this is 8.7 in your textbook. A machine, or otherwise called a simple machine, is anything that will transfer energy from one place to another. So there's all number of machines that we're going to use. This is mostly what you do in mousetraps, as you try to rig simple machines to transfer energy so that you can keep a machine operating. The simplest of simple machines simply redirect a force. So maybe a pulley around one, a rope around one pulley, instead of pulling up, you can instead of lifting something up, you can pull something up or pull a rope down, and it lifts up the weight. It allows it maybe to be easier or more convenient for you to put a force on an object. Other machines multiply the force. So if you were to turn a simple one rope over one pulley into a block and tackle where there's many pulleys, where the rope is tangled over many pulleys, suddenly now it's easier to lift something. So you could hoist an engine out of your car just with your hand, as long as you have it on a block and tackle. It takes a lot of rope to do it, but what you make up for in force, you have to account for in distance. So the work is force times distance. So a machine will usually make something easier, so less force, by making something longer, more distance. And we'll look at this. So the first simple machine we're going to look at is levers. And a lever is going to have some kind of a fulcrum, something over an area that it's going to pivot on. And you're going to have a force acting on this side. So here's your force, and you're going to have a distance. And then you're going to have an output force and a distance. And when they are equal, then the teeter-totter, say, will balance. If you move the fulcrum so that one side's longer than the other, okay, so what'll happen, let's say I have something like this. Well, here is the force, and here's the distance. That means I could have a huge force and a little distance, or a big distance and a little force. Okay, so for instance, this would be like a crowbar. I can put a little bit of a force on the long side, and it move a large force with a short distance. So what you make up for in force, you have to add in distance. If you remember the definition of a force, a work is done when you exert a force over a distance. So you're moving it through a distance. So even though there's a distance here and there's a distance here, so there's a short side and a long side, what's actually happening is you're moving that load through this distance or through this distance. So if you have a very short distance, you're going to end up with a large force, because it's going to be force equals distance equals force equals distance. So if I have a large force on this side and a small distance, I could make up for it by putting a big distance, okay, so the large side, times a small force. So look at this example. If I put a fulcrum to move a boulder, and the boulder is 80 newtons of force, I only have to push with 10 newtons of force as long as I have 8 times the distance. So 8 times the distance means 8 times less the force, because they're going to be equal to each other. Force times distance equals force times distance. That's why you're magnifying the force. You are not having to push at a whole 80 newtons worth. You can push at something more tolerable, something that, 10 newtons, not a big deal, less than 80, but you have to move it a much farther distance. There's a famous saying that if you can give me a lever long enough, I can move the world. The whole idea is that the world may weigh a lot, but if my lever is long enough, then it's reducing the force, and I could move the world with just a very small force if I have a long enough lever. Okay, this is an important concept. Please write this down. The mechanical advantage, I just abbreviate it, mechanical advantage is the ratio, or it's a fraction, of the output force to the input force. Okay, so if I get more force if the output force is big and my input force is small, then my mechanical advantage will have a positive number. It'll be greater than 1. So I want the smallest force that I can put into a machine with the biggest output that I can get. So I want to be able to, say, move my car engine with just one hand. Then I need a machine that can redirect that force. I may have to pull on a rope a long time, but it won't be very hard. And you'll see this in your bicycle. You'll see this in any number of machines. There's machines that you didn't even know were machines are transferring and multiplying forces. So just remember this: output force over input force, or if you want to do output force over input force equals mechanical advantage. Is there an advantage of using this lever? Yes, you don't have to work as hard. You do not have to push at 80 newtons to get 80 newtons of force out of it, but you have to push it over a greater distance. Okay, there are 3 basic types of levers. Okay, a type 1 lever has the fulcrum, this is the fulcrum, set up between the force. Okay, so here's the force that you're exerting on the object, you're pushing it down, and the load. Okay, so this is the load, and this is the force, and the fulcrum is between it. So I'm pushing down. This would be like a typical teeter-totter, okay, seesaw. A type 2 lever has the load between the fulcrum, so here's the load, and here's the fulcrum, and here's the force. So this would be like your foot. Your foot is a type 2 lever. So you could, the force is is your calf muscle pulling up on your heel. So this would be your heel, okay, like that, and it's pulling up on your heel, and you're balancing on your toe. So the ball of your foot, so here would be your toe, the ball of your foot would be the fulcrum, and you can lift your heels off the floor. That's a type 2 lever. The only other possibility is type 3 lever, and that is the fulcrum is at one end, the load is at the other end, and the force is in the middle. So this is how your arm works. It's a pretty inefficient force, but it's how you work with no strings attached to your arms. So you can, your elbow is your fulcrum, your bicep muscle is pulling up on your lower arm, and then whatever's in your hand would be the load. Will you stop the video and draw some pictures of this, please? Now let's look at type 1 one more time. For a type 1 lever, you push down on one end and the load lifts at the other end. So the directions of the input and the output are opposite. You can see this. You've got an opposite output force is opposite to your input force. For a type 2 lever, you lift the end of the lever. Okay, so like this, you lift the end of the lever, and the input forces and output forces are in the same direction. So here's the output force, this is the input force, this is the input force, this is output force. They're in the same direction. And you have the same direction also for a type 3. The output force here and the input force here are also in the same direction. A pulley is like a lever. It is redirecting a force. So if you can think of this rope and A, the little guy pulling down on the rope and lifting the box, it's really like a teeter-totter, only instead of a straight board on a seesaw, you've got a kind of a limp wire. But if I pull down on one, the load lifts on the other. So this would be like a type 1 lever. So a pulley can change the direction of a force, okay? But a pulley also can be used with other pulleys. If you multiply the number of pulleys, you can actually multiply the forces. So look at B. Is there any real advantage here? So the mechanical advantage of A, if whatever the output force is, here's the output force, let's say it's 10 newtons, how much do I have to pull on the other side in order to lift 10 newtons? 10 newtons. Does that make sense? If there's 10 newtons here, there's 10 newtons here. So one pulley is not magnifying anything. There's no mechanical advantage at all. It's not helping anything. It's just more convenient because it may be easier to pull down on a string than to hoist a box. Likewise, you can do a pulley, as in B, where the output force and the input force are in the same direction, so that you're lifting a box attached to a pulley and then you can lift it that way. That may be what you're wanting. Let's look at pulley 2. Is there a mechanical advantage? We've said that there was no mechanical advantage for A, but what about B? Is there a mechanical advantage? Would it be easier to lift that box where one side is attached to the ceiling and then you're lifting the other side? Okay. There actually is. There's a mechanical advantage here. So a pulley over the top of the ceiling is not helping you any. That A is not a mechanical advantage. B, you're actually multiplying the force. So you're multiplying the force the same way that a type 2 lever is multiplying a force. So the input force and the output force are just like a type 2 lever. So this is multiplying the force. But it's not multiplying the force. It is multiplying the force, but it's in the same direction as before. If you were to have 2 or more pulleys, you can change the direction so that it may be more convenient, just like A, but you can also multiply the force. This is called a block and tackle. Block and tackle system. And a block and tackle system is a simple machine. It redirects the force and multiplies the force, makes it easier. So let's review this a little bit. The single pulley acts like a type 1 lever. Okay, so the axis of the pulley itself behaves like the fulcrum, and both the distances are going to be equal, so the pulley doesn't multiply. So if this distance is equal to this distance, then do you see the forces have to be equal. We want the distances to be different so that the forces can be different, right? So if you have force times distance and you make the distance bigger, then the force is going to reduce, and that will be a benefit to you. Okay, so let's look at the next one. The second type of pulley acts like a type 2 lever. Okay, a type 2 lever, remember, where you have, this is like your heel, the input force is coming off the side, and the output force is in the middle in the same direction. So my question is, am I changing the distances? Are my distances different? The answer is yes, because the load is here. This is the load. That means this distance is going to be at least half of the distance in the first case. Okay, so if I move this, as I move this one up, if I move it farther, okay, if I move it farther, that distance will reduce the force. So if the load is in between if the load is halfway between the fulcrum and the input, then I actually am doubling. One input of lift will lift a 2 Newton load. So the mechanical advantage is 2. So the first one, where it's just redirecting over the pulley, these distances are the same, so therefore the Newton forces are the same, and the mechanical advantage equals 1. In this case, you've got the distance is going to be twice as big, so therefore the force is going to be half as much, and you will have an output force of 2 and an input force of 1, and so your mechanical advantage is 2. So this is actually a machine. The second case is a machine. So the kind of clue is to put the pulley attached to the load. If I can have a pulley attached to the load, I'm magnifying the force. So what's happening in the third one? I've got a magnification here. So I've got, this is a block and tackle. It's attached to the load. That means I've got 2 strings attached to the load. And since I have 2 strings attached to the load, I'm doubling the mechanical advantage. This is going to have a mechanical advantage of 2. I've got two strings attached to the load. And then this last one is simply redirecting the force. So this one is not increasing the amount of load because it's not actually attached to the load. All it's doing is making it easier. I don't have to hoist up the box. I can pull down a string, which is a little bit easier. So what do you think? How many strings is attached to this 500 weight? I've got 1, 2, 3, 4, 5. I have 5 strings. That means as I lift it, I'm pulling it 5 times longer because I have to lift each one of these strings. As this load goes up, I have to shorten each of these strings in order to get the load up. So if I'm increasing the distance 5 times, what have I done to the force? If the work done on it is force times distance, and I multiply the distance times 5, I've reduced the distance by 5. And I've divided the distance by 5, and so if I have an output force 5 times more than my input force, then my mechanical advantage is going to be 5. So the kind of the easy way to cheat is if you have a block and tackle, count the strings that are attached to the weight, and that many strings tells you the mechanical advantage of the system. How many times easier is it going to be to lift, but how much more rope are you going to have to pull? You're going to have to pull it 5 times longer, but get 5 times more out of it. So how does a machine use energy? It transforms energy or multiplies force by remember, energy is the same as work. Work is force times distance. And so therefore, if I make up in distance what I lack in force, I can still get the same effect. So a machine is totally useful.